How boring if you didn't get distracted by stuff. Means you're like not interested in anything. All right, you have a lot going on here. I'm just reminding you. Statics 1 is done in the books, graded. Statics 2, we're going to go over that right now. You have this brainstorming thing on your projects. So you got to post 3 for full credit, 3 ideas, right? And then you also got to look at other people's and reply to at least 2.
So what if we come up with like 3 ideas, but then we realize that none of them are good? So we come up
It's fine. It's fine.
Okay, so
Yeah.
do that
No,
all
this
the
is
time.
no commitment. Yeah.
Okay.
And actually, I've had students go for like 2 weeks on a project and then go, this is not happening.
Yeah.
And then switch. So, I mean, you run out of time, right? If you do that, but no, yeah, no commitment. I just want you thinking about it. That's the goal.
Came up with the project idea. I was thinking of building like, since my bed is like back against the wall. And I sleep like with my head against the wall. I wanted to like make like a monitor mount that could like extend and like angle and stuff. Something like that.
Maybe. I guess I'd need more details as far as how complicated it is. I thought you were going to talk about like a bed that folds up against, no, a bed like that goes in the wall type of thing. Those things are so cool.
Yeah, those are beds.
Yeah.
Yeah.
Yeah, some of them are so tricked though. And then you have resume. And then you have these engineering content area things. So you have like, yeah, all this to do.
Actually, that would be pretty cool. Like being able to build something that can like lift my bed up and
Oh,
get more room in my room.
You
Just,
should
like,
look at some of them that are out there. It's crazy.
Yeah.
Like when they flip up, it turns into like a work office station.
yeah.
And then all that kind of just collapses when you bring the bed down. It's pretty cool.
Yeah. people do those
Like
things.
some very fun engineering goes into that stuff. All right. What else do we have here? I think I did something on Friday here. Yeah, okay. So, oh, that's in the wrong class. That goes in strengths. Isn't that funny?
My 2 cents is
That's hilarious. Okay, yeah.
Oh, yeah, for some reason, the like submission area.
I fixed that.
Yeah, like I got it to pop up on accident, it was bugged out, and it was showing me like last semester's. So it had like. a bunch
Yeah,
of
so
work from-
It was super weird. It wasn't hidden. I don't remember what it was, but I looked, oh no, the link. The link here was hidden. So the submission area was fine, but there was no link to it. It was hidden.
Yeah, like,
I'm like, what?
I was
How did
on
that
this-
happen?
I was on the submission area, I think, for this class, and then I switched over to the other class, and it showed me like last semester and everybody else's work, and I hadn't seen.
Yeah.
any of those things.
So weird. It was super weird.
Yeah, Blackboard was about a week or so. Now all my new classes are on like the old.
Yeah, there's some strange stuff going on. All right, I got rid of that. Oh, here's the example resume. I told you I'd put one up. This is not. I mean, it's awesome, but it's not awesome in that I think it's too long. So you're supposed to hold your resume to 1 page or 2. This one's like 4 pages. I mean, Jonathan did a good job. He's super thorough, but I think it should be much shorter. So
Wow,
anyway,
that's too-
it's pretty long.
I have like a lot of different experience, different things, but
Yeah, it's good to condense it though and keep it short and sweet. Just pick the relevant stuff out, type of thing. But I did want to get you one, so it's here. In Blackboard, in the correct class. That's awesome.
I have a question.
Yeah,
So should I include my medical building experience on my resume? Even though it doesn't have anything to do with engineering.
so if it shows responsibility, like that you were responsible for things that were important type of thing, absolutely. Yep. So like, that's what some people say is like, oh, as a cashier, should I show that? That's kind of a hokey experience. Well, were you in charge of money? Like, did you have a till? Did you have to account for that till? Did you work there a certain amount of time that,
But honestly, I got laid off with that experience, so I don't know if it's something I should include on my resume or not, but that is the last job that I worked. So
Yeah, my tendency would be to include it.
And my job for that was awesome. Because I quested,
Yeah. Yeah. So just use that as a reference and don't use the other one as a reference, but I'd still show it probably.
Yeah.
Yeah. All right, absolutely. Yeah. You should email me like officially ask, so then I can put it in.
I put
And if you want me to write a reference letter, I can do that too. Like if you actually get to the point where you're gonna be interviewing or they want references or a reference letter, I can do that.
I think I put references available on request.
Yeah,
I
that's
didn't know if
pretty
they would
typical.
ask.
Yeah,
I would
that's,
ask.
yeah, that's pretty typical. Yep. No problem. All right, let's do this one. Sure.
So I got to the bending stress equation.
Yes.
But I was having a hard time figuring out what the C was, because I couldn't find the diagram with the C shape. So I wasn't sure what I should use for the C, so I couldn't finish the bending stress formula.
That's a problem because I have officially just lost my book. So
I saw the chart that you posted, but there wasn't any diagram with it to show
Oh,
where it was.
really? I
Yeah,
didn't
so
include the
looked on
chart?
internet. I looked on the internet,
No
I
way.
couldn't find it. I couldn't figure it out.
We had the table, and I saw a blank D on it, so I just assumed that was from top to bottom, so I just divided that by two and figured that was C.
It did. Yeah, it's sitting right up here. I cut it off. Yeah. So D is the distance. So a C shape, right, is a C shape.
Yeah.
And D is the distance top to bottom.
Yeah.
So
And
the
that's
C
when you see
distance
like
is,
this, not like this.
no, yeah,
Okay.
yeah. It's in that position. Yep. We would use it in the strong position. Yeah, sorry about that.
So
Oh.
I would just divide D by two.
Yep, divide D by 2. Yep, that's exactly right. That is 100% correct. Sorry about that. Thought I did so good by putting the chart up. Not so good. You got to include the little diagram.
Figure this out, 'cause there must be something I'm missing. I'm just gonna figure it out myself.
All right, so what did you do first? You went through the statics part, right? Yep. And I'm guessing, oh, maybe that pin holds down. Does it hold down? Yep.
Please wait, oh, I calculated it does, but if I'm right.
All right. And then I'm guessing EY goes up. So AX down, or AY, sorry. And AX. Right, we try to solve for those first. So we could do some forces in the X, that's pretty straightforward. Agreed?
Yeah, that's what I do.
AX equals 2 kilonewtons.
Yep.
Okay, perfect. And then how did we get those Y forces? Probably a moment. Okay, so some moment at A. What do we have? We have 2 kilonewtons times
And
10 meters. And that is a negative rotation. Yep. And then we have 3 kilonewtons times 7 meters, and that is a negative rotation. And then we have EY, gonna run out of room, so I'm writing it below, times 10. And that should be a positive rotation. Nothing else. Yeah. Okay. EY equals. Anyone else agree? Comes out positive. So that means EY goes up. So that's good. And if EY is 4.1 up, and we have 3 coming down, we need more coming down, right? 1.1. Yeah, agreed. All right. Now what? Yep. So what's interesting about this thing is when you break it apart, I've always said start with the horizontal or verticals, right? So we can try that and see how that works out. but it may not, like, we might not be able to get it all. So if we use that kind of rule of thumb, I draw the free body diagram of BD, but point E and point A aren't even on BD, right? So everything we just learned, we don't get to use. It's kind of odd. Yeah, but we know we have 3 kilonewtons here. And that we'd have to figure out like where that is, right? So we have to do a little bit of trigonometry. Yeah. Yep.
Yeah, I did B over C equals A over B.
B over C.
And then, well, yeah, but it was like for my triangle I made or whatever.
Yeah,
I
so-
had a triangle
Yep.
inside of a bigger triangle.
Yep.
Yeah.
Yep. So you can do a big right triangle. Correct. Yep. So what is that? 5, 10, 15 up. And then 5 over. 5 and 15. So you can do the angle or you could do ratios, which if you do ratios, there's a little triangle here, right? That also shares the hypotenuse of the big triangle that is 15, 5. So you can set that up 15 meters to 5 meters. That's the big triangle.
Is that the ratio?
Yeah, it's a rise run.
Okay,
Yeah,
right.
yeah. And then since the 15 is the tall, then you'd use the 10 on top, the 2 talls, the 2 rises on top, and then the run, I'll just call it X right here. Right? Because once we get X on one side, we have X on the other side. Correct? So that'll tell us like how far in it is, and we should be able to locate this 3 kilonewtons. So X equals, and actually you want to reverse it all, but
I guess that's not how I did it. It's tan. I did-
yeah, no, you can do sine, cosine, tangent, whatever. Yeah, you can just work it out. So we'll see what I get and we'll see what you get.
I got some of the three.
So I get 3.333 for half.
That's what I got.
Yeah, that's.
Yep,
10.
yep,
I just have to do
Uh,
it.
meters. Oops, not millimeters,
I guess
meters.
you should look at it that way, and you're kind of like skipping some steps.
Well, you don't have to do the sine, cosine. It's, yeah. The key is your 2 triangles must share a side. So these 2 share a hypotenuse. So therefore their ratios have to be the same. So you just set up the ratios and solve it. That's actually an equal sign. So that means the whole distance here is 6.666 meters from B to D, right? 6.666 meters. So that means we can take this full distance down here at the bottom, which is 10, and take the 666 away and get the distance for here to locate this. Does that make sense? It's 3 meters over, right?
Yeah.
So the other way I could do it is like just put this piece in here, because I know from here to here is 3 meters, but I need this piece. What is, what's that distance from here
Why
out?
do you need that?
Huh?
Why do you need that?
I need the distance from here to here.
Oh, that's 4/3, right?
Or you could go from the center of it.
Oh, yeah, you could do that.
Subtract
Oh,
2.
2 meters, sure. That's a better idea, I like that. 2 meters. Love it.
You already know the full distance. So
Yep,
that's 4/3.
for this little distance,
That is.
4/3. Okay. I don't really work fractions very well, so that's 1.33. Right? Excellent. And then what do we put in for these pins?
E1, EX, E1, EX.
Yep, so we have a B, Y, and a BX, and I'm just writing them in a location where it doesn't make a mess out of my drawing. Doesn't matter where you put these, we want to guess at the direction. So I'm guessing these two go up, right, to fight this and also to create moments that fight each other. But as far as these X distances, I have no idea. So I'm just putting them in. Yeah. All right. Now what can we do?
Now I'd be.
Say again? Yeah, moment somewhere, right? It's really the only thing we can do. Summing forces in the Y is not going to help. With two of those. Summing forces in the X, not going to help. So a moment at D or B
I did it.
works just fine. So I heard D first, we'll do it there. 3 kilonewtons times 1.33 meters. And that rotation is plus, yep. And BY times 6.66. Yeah, and that one is negative. And that should be it. Because the other forces all go straight through D. dx, dy, and bx go through it. So that should give us by. What'd you get?
3 over 5 or 0.6.
For BY.
Oh, it's- yes.
Yeah, I got 0.6.
Yep. And comes out positive. Yeah. Yeah, so by is good. Goes the correct direction. So that gives me dy also. Correct? Because now I can sum forces in the y. Yep. So what'd you get for dy? 2.4.
On the same track, so
I love it. Engineering firm is working out. Oh, for sure. Yeah. There are multiple ways to do this. Yeah, so now what? That's, yeah, we got to take something else apart. This is the one we want to do the analysis on, correct? But we really need these two because you don't for what I asked you to do. We could actually do bending stress right now because these two do not contribute to bending, right? They're just all tensile. So you wouldn't really have to continue on. You could go for bending stress here. Does that make sense? Because we have what we need.
So
But if we're doing a full analysis, we would also do tensile stress analysis, right? Which is like, oh, how much is it? Is it just going to pull apart? Because that would be the other way it would fail. Agree with me.
So I was a little confused as to if I was supposed to include the horizontal stresses or not in the bending stress part of it.
And they're all separate.
And
We
so I
treat
was-
them separately.
So I was like looking that up online.
Yeah.
And I was pretty much finding like, no, don't do that.
Right.
But then my husband Eric, he is like all interested in ChatGPT and stuff with his job.
Yep.
So he was curious and he looked it up and it was saying, yes, do it.
yeah.
Well, if you want to do a biaxial stress analysis, yes, you can do it. But not in the beginning of strength.
Yeah.
Not in the beginning, your first analysis, you would not do that. You
Yeah.
wouldn't combine. But it does, like, when you pull on something, it changes that thing's ability to bend and flex, right? So absolutely, it's going to be a combined stress.
Yeah.
So,
Well, anyway, I didn't quite trust ChatGPT.
Yeah,
no, it was right. I mean, it's correct. For the full analysis, you would do a combined stress
Yeah.
analysis,
I was
but
getting very specific though about like what part I was talking about.
Yeah.
And it kept just saying yes to everything.
Yeah,
So
yeah,
I
yeah.
wasn't-
that's super fun to play with, though, I'll have to admit.
It is fun.
All right, so if you went down the road of splitting up and working another one, right? You just pick one of the sides. Like this side here or this side here, right? This piece.
Take either right side because that'll only give us like EX and like C, right?
Yeah, but if you get BX, then you get DX, because then you come back here.
Yeah.
So you can work either side to get the full analysis. All right, let's just do the left side. That's C. That's B, which we've now taken apart. And we know what's going on down here, 1.1 kilonewtons and 2 kilonewtons. And we've got our 2 kilonewton up here. And then something going on up here at C. X and a Y. Correct? All right.
Oh.
Yeah. So then we got to put BX and BY in.
Oh, okay.
You're good. You flip them though.
Oh.
So if BX is going to the left here, it goes to the right here. Because when we bring it back together, it's gotta equal 0. So that means BY here is gonna be BY here, which we know. So that's the other thing, is you have to remember to put in what you know. Don't leave too many things unknown. So if I've got BY at 0.5999, and I've also got 1.1 down, 2 things down, CY's gotta go up, right? That makes some sense.
Yeah.
Yeah, and it's gotta go up 0.6, like 1.7, right? It's gotta balance the system out. Or 1.699. Am I doing that math right in my head? I'm a little worried about that.
1.7 kilonewtons, that's what I got.
I gotta read it all.
Yeah, I'm gonna write 1.6999. Keep my accuracy as long as I can.
Yeah, I just gotta read
So that's good. If we've got these two, CX and BX unknown, we've got 2 kilonewtons going to the left. I cannot sum forces in the X. I have to do a moment. Okay. Because these are the only 2 left that I need. And this one more important than this one, because this one then I can transfer right up to here, give me DX, that'll be solved. Really? I don't know of any scheduled. No, exactly. We're gonna find out.
In this building,
Yikes.
please operate and leave the building utilizing the nearest exit or fire exit stairway.
An emergency, that's not really very informative.
Not use the elevator.
Oh, I'll pause this.
Attention, attention. An emergency has been reported in this.
Yeah. Right.
Yeah, that's really crazy when I see people walking on the street.
Oh, I could be over 1.
Yeah, that's.
I don't like to not be
But
able to
like,
hear
you
what's
have
going
to
on.
hear, yeah, you have to hear like people coming up. Cars coming up on the sidewalk or.
I like transparency mode on Google and stuff, so it has like a mic from the outside, so you can see.
Oh.
Like,
Yeah, mine have that. I think it's called like ambient mode.
yeah.
Where it makes everything look like louder.
All right, so I'm gonna sum the moment about C. Because I really don't care what's going on at C, I want BX. Okay, so that's the strategy
You
there.
got C that, oh wait, you got CY?
Got CY, yeah, just by summing forces in the Y. There's only 3 of them. Yep. So gonna do a moment at the top. So that's gonna be 2 kilonewtons times 5. This one. And then BX times 10. And the 2 kilonewtons, let's see which way that rotates. That's positive. And BX is positive. The 1.1 creates moment. And that is a distance of 5, correct? Excellent. And that rotation is counterclockwise, positive. The 2 kilonewtons, there's a lot of them. The 2 kilonewtons times 15, and that rotation is negative,
Oh,
right? Is that right?
I might have just-
Clockwise, yeah, negative. And then the tough one is BY. We just need a distance. Oh, sorry, BY is 5.599. And we need that distance right there. So this whole thing is 6.66. So I think we take it. Yeah, it's the half distance, 3.33, yep. And its rotation is positive, counterclockwise. Whew. That's why you stay away from those angled members. That's for sure. But we couldn't. If we actually wanted BX and DX, this was the only way to get it. So the only unknown in that equation is BX. So BX is positive. We want to leave it there and move all these other things to the other side, which changes their sign. So, and negative.
If you're gonna get an email later, explaining what that line is.
Sometimes we do get those, yeah. You won't. I don't think you will as a student. But I will as a faculty, so I'll share. I get 1.2502.
Yeah.
I think it's because your guys is rounding and stuff.
Yeah.
I should have-
Yeah. Yep, that's good. So that's BX, comes out positive, meaning that BX is the correct direction here, which means BX is the correct direction here. So that's good. 1.25002. That's what I got. And now that I'm back up here at this member, there's, yep, oppositely directed. So now we have that member solved out. We could get a tensile stress, but we can also do our bending stress now.
So the C on the C channel is just in the center, horizontal center.
Yep, that's correct. So I'm going to redraw this member and put in the forces that I need, which is BY, 3 kilonewtons, and DY.
Can't see what you're doing.
Okay, I'm just redrawing this thing. If I do that, then you won't see the other part, but that's all right. I'm gonna move it all in a second, so. BY is 0.5999, right? And this whole member is 6.66 meters. So that's really what we need to do our bending stress. Our single axis bending stress. And we need to know it's a C shape. And that's structural steel. So once we get our maximum moment, we can go for our bending stress. S sub B equals MC over I. We're going to neglect the weight of the beam. The shear diagram. This is going to be 0.5999. This is going to then drop down 3 to 2.400. So 0.1. And then it returns. So that's all good. Then the moment diagram's pretty easy. It's got plus slope and it's nice and consistent. So that's linear plus slope. And then it's got negative slope and the negative is bigger, so it's steeper. And that gives us our max moment location. And we know that because it crosses 0 here. And we know the moment's equal to that area right there. So 6.666. Careful. Because the distance here from here to here is 5.333 meters. So it'd be the 5.333 times the 0.5999. 3.199 kilonewton meter. And it's positive, meaning that the deflection is kind of concave up.
How do we know when it would be like, when we would actually make the line on the moment diagram? When we would make it more curved rather than more straight?
If this is not linear. So since this is linear, the slope does not change. And the only way a slope cannot change is if it's a straight line. It's inclined, right? So if this distribution looked like this, right, and then came down and over and up or whatever, anytime you see a slanted line here, then that creates some kind of curve because the slope changes, right? Gets from little positive to big positive. And that's where it's going like this. Oh, I should start it flatter. Little positive to big positive, right? So that means this would be, yeah, the progression would be curved. That makes sense? Yeah. So if it's horizontal, it's going to be straight line slope. If it's straight line slope, it's going to be some kind of curve. Excellent. So now I can run my equation. I know my moment is 3.199 kilonewton meter. And I know my depth or D value of my C channel. What is that?
Oh, C is 152.5.
So what was D? Give me that first.
305.
305 millimeters, and that is the total height of your C shape. Yep. So I can put it in 305 millimeters over 2. Now, we have a meters millimeter problem immediately. So we're gonna have to solve that. What's the inertia? You can look that up, right?
53.7.
That's what I got.
And then what's the unit?
Millimeters.
Yeah. So that means that we have millimeters to the fourth, we have millimeters here. We need this meter to go to millimeters. So we have millimeters squared above. That'll change the overall equation to kilonewtons per millimeter squared, which is a pressure. That's what we want.
We want. per millimeter, not
Correct.
I think just 9 by 1 of it.
Yeah, so then if you want to write it out, it's 1,000 millimeters per meter, and we want those meters to cross. Right? So that'd be a good unit analysis there. So.
Probably then on yield.
Careful, there's another table there for the SI system. Yep, look in the back of the book, you should be able to find SI equivalents for yield stress. I don't have my book. I don't even know where my book is. That's what's really sketchy. Yeah, I know, it's not in my car, it wasn't on my desk at home, I'm like, what, oh. Bet it's in my office. I never use my office, but I was up there the other day. I want to go look, unless somebody's got the book.
I don't know. I wish I did have the book. I feel like buying it.
Yeah, I got half of what you got. 9,000.
You did too? What? What did I do wrong? No, well, I don't think I did, but maybe I did. 305. Maybe oh, I just hit the times button instead of the multiply or divide button right there. Maybe I did that. Yeah, something feels different. 9,084. Okay, sorry. That's why we do this as a group.
Yeah, so what messed me up was when you like redraw your reaction.
Yep.
That one beat, I forgot to switch the directions. of
Yep.
the arrows that I did. That kind of-
Yep, that'll screw it up. The other thing that is easy to do is like when you're drawing this, when you're isolating it, like you forget the 2 kilonewtons or something, just leave a force off. Like, because you're so focused on the pin forces that you leave like external forces off. So yeah, it's really easy to make those kind of mistakes. Yeah, so anybody find the table in the back for the SI?
Oh, I didn't come through it.
Because I don't have a book. I can't do it.
I have a screenshot of it.
Yeah,
Let me-
because we're looking for structural steel, just regular mild steel. 836, yep. I could look online, probably find it.
That's right here, I got it. Okay, what are we looking for?
836 feet.
Yeah, properties of it.
Oh, wait.
In the metric version. Yeah, so they give it in, here's one. I have found this, right? Tensor yield strength, 836, 250 megapascals. Ooh, so we got to figure out like what's a Pascal. Yeah,
So would that would be on the C-shaped channel.
no, that's going to be in material properties. Yeah, so check this out. Yeah, one, I'm going to write it down and then we'll go back to screen to the viewer. 1 PA equals. We're close to those units, but we're not at those units. A Newton meter squared. So they give the limit, the yield. I'm going to just write SY as 250 MPa. And 1 PA is a Newton per meter squared. So let's get our number to a Newton per meter squared. So that means we got to get the kilonewton gone. 1 kilonewton equals 1,000 newtons. So now it's gone. And then we got to get millimeters. So there's 1,000 millimeters squared per meter squared. So this is important. There's 1,000 squared millimeters squared per meter squared. Yeah, big number. Right? Because that gets rid of the millimeters squared, but you cannot forget to square the 1,000. Yep. There's 1,000 newtons in a kilonewton. That's the first one. So we got to take our number and multiply by 1,000 and then by 1,000 squared. Yeah. Which is a solid million. Yield stress, which is actually different than a bending stress. But if you can't look up a bending stress, we can use a yield stress. We actually use a percentage of it, but for now, not going to go there.
The 9.08 times 10 to the 12.
That's what I get. Yep. And that's pascals, but the limit is in megapascals. So what's mega stand for?
Oh, no.
It is a million. Yeah, it's 6 zeros or 6 places. No, your limit's in megapascals. We need this in megapascals.
Oh,
So since this is such a giant number, we can take 6 away and then that makes it megapascals. So 9.08 times 10 to the 6 megapascals is what we just calculated for a bending stress. Does that make sense? That is like 1,000,000 times bigger than 250 megapascals. Right? So this is the calculated stress. Yeah. And this is the allowable yield for the material. So what do you think is going to happen here? Something very bad. And it happened a long time ago. Like, it's not even going to come close to carrying this load. Our little C shape. Yeah,
So
that's
the
exactly
answer
right.
for
Yeah, that's the bending stress answer. Yep. What's the bending stress? But anytime I ask you or anyone asks you what the bending stress is, the only reason you would calculate that is to determine if it's good or not. So you really should take your bending stress and compare it to something. If you have that something, sometimes they don't give us the material in these problems, which is terrible, I say. Because really the only reason we would ever do this is to compare it to something. Like, is this good or bad? Like, is this going to work? Like, no, this is not going to work. Solid no. Like, I don't know if they make a C shape big enough to carry that load. Right? Anyone have a feel for how big a Newton is? A Newton is not too big. A kilonewton. Yeah. A Newton is about 6 pounds, 5.8 pounds. Okay. But a kilonewton then would be, yeah, 1,000 times that. So we're talking 18,000 pounds essentially on this thing. And that little C shape was little. So it's not carrying it, no way. All right,
Is this missionary?
should be. Let's check. Yep, it's there.